Okay, good afternoon, everyone. Welcome to this session. Next up, we have Halfdan. He's going to talk about geospatial data analysis and visualization in Python. Let's give him a warm welcome.
Okay, thank you. I'm going to set a timer for 27 minutes. So let's hope I finish. Right, so as I was introduced, my name is Halfdan, and I'm going to tell you about geospatial data analysis and visualization in Python. 日本語も大丈夫だから質問があったらぜひ言ってください。ちょっと簡単に言ってくれたらうまく回答できると思います。So I work in a Japanese company called Digital Garage, where I'm in the research and development lab called TG Lab. And I don't know, you may be wondering what is actually geospatial data visualization. So geospatial data is just any data where you have coordinates associated with some or all of the data points. So in this talk, I'm going to basically show you how to make pretty looking maps using Python. And I'll go a bit further and show you how to make interactive maps in Python. So sort of the outline of the talk, first we'll make this map. I rely on internet connectivity for the map tiles to be loaded. So the network may be a bit congested at the moment, but I think you sort of get the idea of what's going on. So this map that I just showed you is actually really simple to make. So I will show you some of the code. Or rather, yesterday I saw that it's almost impossible to see code on the slides. So I'll just jump over most of the code. Besides, my talk is probably going to be pretty long anyway. So after that simple map, I'll show you how to make a much more detailed map. So this is a map of Shinjuku, and you can really see that we have much more detailed spatial resolution of this map. And I actually had to do some coding to get this. And then finally, I'll show you this kind of map with this intriguing looking slider up here. And if we try to move that, you'll actually see that it's changing the data over time. So I think this is pretty cool myself. So yeah, so I'll show you how to visualize the geospatial data over space and over time. So those were my two interests when I began this project. So you're probably wondering what data I'm plotting. So the company I work for, has tight connections with Tabelog. So our team was very lucky that we got a lot of very nice data from Tabelog. So what I just plotted were the average restaurant scores for all the different areas. So the data, or at least a tiny bit of the data, looks like this. You can see the first two columns here are the latitude and longitude, so the coordinates. So you can place the data points on a map. And then we have some average score and review counts and so on. So this is actually exactly what we need to make a map, right? So here's my attempt at a joke. So when I started looking at this data, one of the first things I did was to calculate the geographical mean of all the restaurants in all of Japan. And I ended up in a place called Obama. So I don't know if there's some secrets going on there. Yeah, so that was, shocked cat. So I'll get into the actual code soon, but just a bit more specification. I'm going to show you a specific type of maps called a choropleth, and this is very hard to pronounce for me. Choropleth. In Japanese, it's kaikyu kubunzu. So I don't know if it makes sense. I'd never seen this word before. But really, a choropleth is just kind of map where you plot, you have some areas and you plot the borders, and then you give a color to each area, and the color reflects some statistic that you want to show. So this is a choropleth. Here, red means high scores, and yellowish means low scores. So I like choropleths a lot because they're very easy to interpret. If you just look at this, you get a very quick overview of where the good restaurants are and where the bad ones are. And they're also quite pretty, I think. So this is like really the two main things you want to do when you do data visualization. Easy interpretability, and it has to look cool. Otherwise, you get no investment. So there are actually a lot of different ways you can plot on a map. I'm not going to go into it, but you can read more here. And I just realized that you cannot actually click this link, so I'm going to upload the slides. So why do I want them to be interactive? Well, basically because I think it's fun, you know, and also because I wanted to make a tool for discovery. If you just have a statically rendered map, you can't really do anything with it. You can just look at it. But if you have this interactive map, you can zoom in, you know, go to your own neighborhood, click on it, see, get some more information. I mean, here we don't get a lot of information. It just says Nakanoku, but it's really easy to add more to this pop-up box. It's just an HTML pop-up box. So all of this we'll be making in Python, okay? So first we collect the ward boundaries, so the area boundaries. These are the area boundaries. They are just the lines that separate the areas. Where do we get them? Well, of course, the internet, stupid question. So I just went to Google and searched Tokyo boundary data, and I found a place where I could download it, so I just saved it to my local disk. But actually, there's a really nice library that can do this for you, and I'm going to talk about that as well. So if we open the data, we see that it's just a dictionary with 3 keys. And if we print the features, we can see that there's a property dictionary in here with some information about Adachiku, and then a long list of coordinates here. So just a long list of points, right? So this is a format called GeoJSON. I don't know if you're familiar with that. There's a lot of different formats for representing geospatial data, but GeoJSON is like the simplest and easiest one to use. It has some drawbacks, like the files get pretty large, but I like it because it's simple. So if we take a look at the file size, it's 6 megabytes, which is kind of a lot, right? Because it's just, you know, a bunch of lines for 50 or so areas. So where does all this data go? Well, if you zoom in, you can see that the borders are really quite detailed. And every time you have a curve, let me see, here there's a nice example. When you have a curve, if you zoom in, you can really see that it's just a bunch of straight line segments. So there's no parameterized lines or anything like that. It's just point to make lines. So after I downloaded this, I was like, you know, I'm used to pandas and nice tabular data. I wish there was a way to efficiently and conveniently handle this geospatial data. And of course there is. There's a library called Geo Pandas, which you can just install, use it like this to read your GeoJSON file. And you get a very nice looking data frame where the properties have been put in regular columns of the data frame, and all the coordinates have been converted into this funky looking polygon objects stored in a geometry column. So let's take a closer look at this geometry column. So if we print the type, we can see that it's just, well, it's just that it's something called a shapely geometry polygon object. So shapely is another Python library. I'm talking about a lot of Python libraries here. Shapely, you can do stuff like you have points, lines, and polygons, and you can easily calculate intersection between lines or overlap between polygons and stuff like that. I don't know if I'm talking enough into the microphone. One thing that I really like is that it's integrated extremely well with the plotting backend in Jupyter Notebooks and the Qt console. So if you just print the object, the polygon object, it actually plots it for you. So this is very nice as a kind of sanity check when you're doing, you know, work. And one important point is that the workflow with Geo Pandas is more or less the same. Well, it's pretty much identical to that of the Pandas data frame. So if you're used to Pandas, it's very easy to go start using Geo Pandas. So Geo Pandas is a really nice library. And I want to, applaud the authors of this library. I didn't make it, but yeah. So now we have the boundaries and we can hold them in our geodata frame. So how do we plot them? It's super easy. One-line command. Here I take all the areas with Q in the name and use plot, and we get this fairly nice looking plot. This is very nice when you're doing analysis. It's very fast to make, but it's not interactive, right? We really want something that can run in the browser. So there's another Python library called Folium. This is the logo of Folium. So Folium is a Python library for making interactive maps, and it's built on a JavaScript library called Leaflet, and Leaflet is built upon D3, which I'm sure everybody in this room knows. So let's try to make a map with Folium in 2 lines. So these 2 lines, you make the map, okay? And then we save it to an HTML file, and this is what we get, the map that I showed you before. 2 lines. So now we have the boundaries and we have the restaurant data, right? So now we have to assign the restaurants to each of the areas. So in this case, it was pretty easy. I just used the zip codes to assign all the restaurants. And once I did this, the data frame looked like this. Now each restaurant has a ward. So when you work with data or like do engineering in general, I guess it's very nice to do sanity checks all the time. So a nice sanity check to do here is to calculate the geographical mean. So before it was in Obama, right? But now it's in Meidaimae, so the center of Tokyo, more or less. So now we can calculate the statistics. We do a standard group by and aggregation. In this case, I'm calculating the mean. And this is the result we get. Here I have sorted by the average score, so it's sorted by in descending order on this score. And we can see that the area in Tokyo with the best restaurants on average is Kunitachi, which I think makes sense. I think there's a lot of rich people there. So, and if we go to the worst restaurants, we end up in Chofushi or some other areas. I can't read this kanji, but Komai. Ah, okay. It's next to Chofu, I think. Yeah. So, and it's quite a large difference, right? It's like average score of 3. So Tabelog scores goes from 0 to 5. So Kunitachi has an average score of 3, and Chofushi has an average score of 2.5, and it's calculated over quite a large number of restaurants. So we can say that there's really a statistically significant difference between the two. Probably I'm going to get bashed for saying this later, but anyway. So let's put it all together. We define a color map and calculate colors for the average scores, and then we use Folium again to plot our map. And this is what we get, okay? So, all right, I took a screenshot. This is not actually interactive. Oh, it is? Anyway, so this is the map we got. So it was quite easy to make, actually. So now we have a toolbox where we can hold our geodata in Geo Pandas, and we can plot it using Folium. So at this point, I took a coffee break, another coffee break. I have quite a lot of those. And I started thinking that wards are kind of large, right? The cities are kind of large. And the map that we just made is really not very useful for discovering new restaurants, discovering new areas, because the wards are simply too large. So the question that I started thinking about is whether or not it's possible to find boundaries for smaller areas. And so how about the zip codes? Okay, so the data for the zip codes in all of Japan, you can download it, and it looks like this. But one thing I didn't like about zip codes is that they are still administrative boundaries. So they are just, boundaries of the city decided by the post office. So it might not be very useful to our application at all. And besides, postcodes can be quite large, or zip codes, I call them here, but they can be quite large. Like, up here in Hokkaido, you can actually see, like, okay, it's difficult to see here, never mind. But they can be very large. So in general, what do we do when there's no GeoJSON for areas that we want to visualize? And I started thinking, and I decided that I wanted to calculate city blocks. So what do I mean by city blocks? Well, they are areas that are encapsulated by roads. So this is a small part of Daikanyama, an area in Tokyo. And you can see the black lines here are the roads. So the city blocks that I wanted are just these areas here that are sort of encircled by roads. So I'm going to argue a bit why I think city blocks are nice. Well, first of all, they're kind of the smallest unit in the city. You can't really go lower than that, apart from maybe building footprints. But they also really reflect the topology of a city because they are defined by the actual street network. So, which also means that if we can get the street network, we can use that to calculate the city blocks. So, where can we get the road data? From OpenStreetMaps, which I also think most of you know. So OpenStreetMaps, just in case, is the largest open map on the planet, and it's sort of Wikipedia style in that anybody can go there and edit the map. So this is a screenshot from OpenStreetMaps in Shinjuku. It has different layers. And this is the transport layer where you can see all the train line and the bus lines as well. And here's the bicycle layer from Copenhagen. So Copenhagen, where I'm from, is famous because you can bicycle everywhere really easily. And in the bicycle layer, they show all the bicycle shops as well. I think that's probably useful if you go somewhere and your bicycle suddenly breaks down and you need to get it fixed. I don't know. So anyway, all this data is free, and we can download it through an API, but there's another really great Python package. I know I'm putting a lot of Python packages out there, but this really great Python package called OSMNX, which stands for OpenStreetMap Network X. Network X is another famous package I'm sure most of you know. So we can, for instance, use it to get all the street networks from Shinjuku. It looks like this. Or we can get it from a point. So here I get also from Shinjuku within a 1 kilometer radius. And all the data that OSMNX, or OX, I'm just going to call it OX because it's much easier to say. So all the data that OX downloads is stored as a Network X directed graph. So roads are the edges in the graph, and the intersections are the nodes. Okay? So OSMNX has this nice Folium integration, so you can just plot. Okay. It's zoomed out a bit. Fortunately, I took a screenshot. So if we zoom in on that, you can see here it's the street network overlaid on a base, on a map. So OSMNX can be used with Folium. And because all the data is stored as a Network X graph, you can also use it to calculate some useful statistics. Like for instance, in this small road network, we can see that there's actually 42 kilometers of road just in that small part of Shinjuku. 10 minutes, okay, stress. So you can also use all the Network X algorithms on the street graph. For instance, here I use it to calculate the betweenness of all the intersections. I don't really use it for anything, but I'm just showing you that you can do that if you want. So Ox is a really another really great tool for our toolbox, and it's written by a guy called Geo Pandas. I'm linking to his paper in the end of this talk. So we can easily get the street data. So now we can calculate the city blocks, and it really just is a problem of finding certain kind of cycles in the city graph. So I'm running a bit low on time, so I'm not going to go into the algorithm too much. But mainly, I couldn't find an implementation anywhere because none of the cycles algorithm in Network X did exactly what I wanted to do. So I found an algorithm somewhere and decided to implement it. Have some fun and do some code. And so basically, the algorithm is very simple. I'm just going to illustrate it really quickly. You start in one node, and then you just pick a road in random, and you keep going left, 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 until you end in the place where you started. And then the rule is that you can never walk on a road. Let's see, you can never walk on the same road in the same direction twice. So it's a fairly simple algorithm. And I made this, it's not my proudest code. It's a recursive implementation, and it's sort of difficult to parallelize. So it was a bit slow, but fast enough so that I could calculate city blocks for pretty large areas. This graph here has around 7,000 city blocks. So, I mean, it runs relatively fast, but it could definitely be made faster. So, I also have a part of my talk where I talk about how I speeded up the calculation, but I'm just gonna skip over that fairly quickly. So one of the main ways to speed it up was to limit the recursion depth, which means that you can only find city blocks which are enclosed by, if we limit the recursion depth to D, we can only find city blocks encircled by D roads. So if we limit it to 10, we find only the very simple city blocks. So we really have to crank up the recursion depth to find the more complicated city blocks. The next sort of major speed up I got was from using a simplified graph. So basically, the graph where you remove all the nodes of degree 2. Okay? So if you look at this and compare it to this graph, you can see that there are not so many blue dots in this graph, right? It's because a lot of the nodes have been removed. So fewer nodes, fewer edges means a smaller graph, so less graph to traverse for the algorithm. Okay, so the problem is that this kind of changes the shape of the city blocks that you get. So this is the city blocks from the non-simplified graph, and you can see that the city blocks align perfectly with the roads. But if we use the simplified road networks, we get some more, not so pretty city blocks. So it depends. If you need speed, you have to sacrifice accuracy. That's quite common, right? So now we can calculate the city blocks, and yeah, I'm just gonna skip this. This is just how I assign the restaurants to the areas. But once we have assigned all the restaurants to the areas, we can calculate statistics and then finally create this map that I showed in the beginning. So now we are really getting to a place where we have a tool where we can see some tendencies, for instance, that on average, for the big roads in Shinjuku, the closer you are to the roads, the lower the average score is. And you have to go to sort of like Yoyogi, say, to get nicer restaurants. So let's see, I think I have 5 minutes left. So we can also plot the best restaurants and the worst restaurants. So you can really just plot whatever. Once you have grouped your data, you can plot whatever statistics you want. And then finally, you remember in the beginning I showed you 3 maps, right? So the really simple one, the more detailed one, and then the one with a time dynamic component. So the fact is that, you know, people review restaurants all the time, right? So the average scores will go up and down, kind of like this. So it's time dynamic data. And Folium can make animations like this. That's already in the library. Well, this is Leaflet, but it's the same is possible for Folium. But I wanted to animate my choropleth. So I had to make my own plugin for Folium to do this. And the code is long, but the main thing I want to show is that the usage is more or less exactly the same as when we made the first choropleth. We call the time dynamic GeoJSON class, give it our Geo Pandas data frame with a dictionary that defines the styles, the colors and opacity and so on. And this is the money shot, okay? So you already saw this, but I just want to show it again because I kind of like looking at it. Yeah, so you can like see how data changes back and forth in time. So, and I plan to submit this in a pull request to Folium, so if you want to make the same maps, that should be possible fairly soon. So the summary is that I have shown you 3 high-level libraries. It's sort of warm in here, I think. I don't know. So I've shown you Geo Pandas, which is really sort of the basis of doing geospatial data analysis in Python. And to the guy who talked about Dask. So please, if you could make a Dask-enabled Geo Pandas data frame, that would be very nice. Oops. Okay, 3 minutes left. The second library, OSMNX, which you can use to download and manipulate the street graph. And then finally, Folium for making interactive maps. But just remember, there's a lot of other libraries being used by these 3 libraries, and to, you know, to how can I say, for the more advanced use cases, you really have to dig into those libraries as well. But yeah, and then my own contribution, I implemented the algorithm and made the Folium plugin. And so finally, this is a joke that's really hard to pull off. All the slides, all the presentations I saw yesterday, I think, had this, you know, why Python slide, right? So I just want to say, why JIS in Python? Because we can. Okay. Yes, people laughed, yes. Yeah, okay. So I just want to end on that note. So thank you very much for your time.
Okay, thank you, Halfdan. We have time for 1 or maybe 2 questions.
Yeah, please.
日本語でもいいですね。気軽にどうぞ。
Yes.
So for the value updates, are those things that are already in the data frame, or can you dynamically change values in the data frame to reflect that on the map?
No, this is no, basically no. This is you call this on the data frame with the values that are there already, and then it's rendered to an HTML file. Yeah. Samuel, you have to ask questions. By the way, Samuel, who sits over here, he helped me quite a lot with some of the code. So thank you, Samuel.
So maybe this is a yes/no question. Do you think the 3 libraries that you're using are production ready?
Yes.
I love short questions. Thank you very much.